Hello, everyone. I'm Jean-Christophe Hamilton, and I'm a researcher in cosmology in France at the APC laboratory. And today I'm going to discuss the use of bolometers for cosmology. In fact, I'm the principal investigator of a project aiming at detecting the primordial B modes from the cosmic microwave background. And we're trying to detect a very small signal, about a few tenths of nanokelvin on a background of 3 Kelvin, polarized signal. And for detecting such small signals, we use detectors called bolometers, which I will explain today in very light details, nothing too complicated. So the outline of the talk is given here. First point, we will discuss what are bolometers, and then we'll see how we use them for cosmology, and this will be very basic considerations. Then we'll get a little bit more technical, trying to understand the physics of some kind of bolometer called TES, transition edge sensors. We'll see how we can fabricate them. The process is rather complicated. Then we'll look at the details at the noise in a transition edge sensor. And one of the issues with bolometers is reading them, and we'll discuss that shortly at the end. We'll see some examples to finalize, and then we will conclude. Okay, so let's go into the talk, and let's ask ourselves what is a bolometer. And as you will see, there are some kind of magic tools in the experimental physicist toolbox. So the word itself, bolometer, comes from the Greek bole and metron, and it's self-explanatory if you speak Greek, which I don't. So bole means ray of light, and of course metron means measurement. So basically this is a device that is designed to measure light. It actually measures more than light, but anything that dissipates energy in the medium. So they were invented by Langley, an American astronomer and physicist, in 1878, and he invented them to study the radiation from the sun. Well, the principle is rather simple. You have light that is absorbed by some material, which is connected through a thermal link to a heat sink, so that the absorber here is at constant temperature. Then when the light comes into the absorber, it heats the material, and we can measure the temperature increase of the material, which will soon go to its initial temperature thanks to the connection to the heat sink. Okay? So the good thing here is that they're sensitive to any kind of radiation, which means that they're very large bandwidth, which means that you can accumulate photons over large bandwidth, which is a good thing. They have a fast time constant, which, as we'll see in a moment, is driven by the thermal link to the heat sink, as well as the mass of the absorber. They have impressive noise properties that we will try to study in a moment. But basically, this is related to the stability of the material, so meaning that the colder the material, the lower the noise. One of the nice features of bolometers is that they work fine with high background, meaning that if you have a lot of light coming in, it means that the temperature of this absorber will be slightly higher than with less light, but the ability to measure radiation is still there. Okay? So as often in astronomy, Herschel was there before anyone, and was ahead of the rest of the universe. So as you know, Herschel was an amazing musical composer. He built amazing telescope, discovered a lot of objects in the sky, like Uranus, Oberon, Titania, Enceladus, and Mimas, which are moons of Saturn. He also discovered that the Mars ice caps are variable with time. He investigated and assumed for the first time the flat shape of the Milky Way. He made the first catalogs of nebulae, like the NGC catalog. And it turns out that in the early 1800s, he was a pioneer of astronomical spectroscopy. And what he did is that he used a prism, as can be seen here, to disperse the light into colors. And then he placed thermometers in front of this light in order to measure the amount of light in the different colors. Well, that's the first bolometer, actually. He remarked that beyond the red color, the temperature was still increasing, and that was the discovery of infrared radiation. So, as you can see, bolometers were used a long time ago to make great discoveries. So, why would we use bolometers in cosmology? Well, let's ask these people that are specialists of cosmology, and they will tell us. So, there are two main categories that we use with bolometers in cosmology. The first for dark matter detection, there are massive bolometers, and the second one for observing the cosmic microwave background. So, I will go into much more details about the second one. But just a few words about the first one. You know that dark matter is about 86% of the matter in the universe and about 26% of the energy in the universe, which is not negligible. It's very hard to detect because what we think is dark matter is that it's a kind of matter that only couples through gravity to the rest of the universe. So they could be supersymmetric particles, they could be actions, there are many models. But for sure, what we know is if it exists as particles, there are particles that do not couple much to ordinary particles. But it is possible that there is elastic scattering with the nuclei, and in such a collision, there would be some energy deposited in the nucleus, which would recoil, and this recoil of the nuclei would dissipate energy in the material. So we could detect this dissipation of energy. Of course, there's a very high background from a lot of other interactions, but it is possible to use them. And so such very massive bolometer, massive because you need a lot of nuclei, they're used to measure such a signal. So it's been used for 20 years and never detected yet. The second type of bolometers are used for CMB observation. So the CMB is a relic radiation from the Big Bang, emitted about 400 years after the Big Bang, and it appears to us as a black body at 2.7 Kelvin. You can see the spectrum here, which peaks at 150 gigahertz, about 2 millimeters, and that's a map of the fluctuations of the CMB that we are measuring and from which we extract a lot of information in cosmology. So the thing is that such a cold black body has photons with energy of a fraction of an MeV, so very little interaction. It's less than a picowatt deposited in the detectors, so very, very little energy. And there's a lot of background from the rest of the instrument, from the atmosphere, and so on. Furthermore, there is no specific spectral feature in that spectrum. It's just a black body. So you need a high sensitivity, very large bandwidth in order to integrate over a very large range of frequencies. And above 70 gigahertz, bolometers are very much used and are now the best detectors for these observations. Below 70 gigahertz, one can use antennas and amplifiers with higher noise. Actually. So the takeaway message of this introductory part is that bolometers are very good for detecting small signals. And if the base temperature of your bolometer is low enough and that there are small thermal fluctuations, then you have basically very low noise. They're allowed to detect over large bandwidth because they detect anything. And that's not the case with other kind of detectors. And they can actually detect anything that deposits power in the absorber. So it can be light, cosmic rays, so you have to be careful. They detect on top of a high background because they detect everything, but the background just shifts the base temperature, which means that you can still detect the signal, but if the background fluctuates significantly, that implies some background noise that we'll discuss in a moment. Okay, so now let's go into more technical details. Let's go to Mordor together, but remember that there is some hope in this world, Mr. Frodo. So we will focus, as I said, on CMB bolometers, and there exist basically two main types of bolometers. In both cases, the idea is to measure the resistance variation with temperature, and you will polarize your bolometer with voltage or intensity, and then you will measure the intensity or the voltage. Sorry, this is badly written here. First type, thermistors, are semiconductors, and they're in normal state. And basically, you have the resistance that reduces with higher temperature. So when you go to low temperature, the resistance increases, and basically the amplification or the response of the bolometer, which is given by this, is between -5 to -10, something like that. One of the issues of these bolometers is that they're not so linear. Second type of bolometers are the transition edge sensors. In that case, we use a material that is exactly in its transition from superconducting to normal, which means that we have a very high slope here, which means a high amplification, which is of the order of 100 to 1000. They're much more linear, as we will see in a moment, and they're basically now the standard CMB detector as of today. Okay. So let's investigate a little bit the physics of a transition edge sensor. It's very simplified. Okay. So you imagine that you have radiation coming into your bolometer. So that's the optical power that is deposited here. You have the absorber that has a calorific capacity C. You have the thermistor here, which is polarized. In the case of a TS, it's polarized in voltage. And so you have some electric power, which is here, which is V squared over R, of course, at this temperature. And this is linked with thermal bath through this thermal link G, okay? And G basically tells you what is the power, is the connection between the power dissipated in the bolometer, the temperature of the bath, and the actual temperature of the bolometer when it receives power. The received power increases the temperature of the bolometer, and this difference is basically related to the dissipated power by G, okay, in watts per Kelvin. C, the heat capacity of the absorber, is in joules per Kelvin. So finally, if you make the ratio between these two, it will give you the typical time to dissipate some incoming heat, C over G. So here, just to be sure we understand, there's a perfect analogy with an electrical RC circuit, okay? C is the C of the capacity, and G is the conductance of the material, which is 1 over R. So the time constant is RC, which is C over J in our case, okay? So this is really thermal RC circuit, a bolometer, right? So one important thing in the physics of a TS is what we call the electrothermal feedback, okay? So one important thing is that the TS has to be voltage biased, and you'll see why. So what happens is that when radiation is absorbed by the bolometer, the temperature of the bolometer will increase, okay? And as we have seen, this difference here between the temperature of the bolometer and the temperature of the bath multiplied by G is the power that is circulating in the bolometer, okay? So because the temperature increases, we're in the normal to superconducting transition, then the resistance increases. But if you remember that the electrical power that is in the bolometer, and because the bolometer is biased, this electrical power is V2 over R. So this means that because V is constant, R increases, well, the electrical power decreases. And that basically compensates the increased optical power coming into the bolometer in such a way that the total power in the bolometer remains constant. Now, if you come back to this formula, this remains constant. This is a constant, and this is a constant as well. This means that the temperature of the bolometer actually is constant. So as you see, we have a way of stabilizing the bolometer in the transition. This is known as the electrothermal feedback. So when a TS is inside the transition, it has constant temperature, basically whatever incoming power. So it's not exactly whatever incoming power, because if the optical power comes in, increases too much, because the total power is constant, that means that this guy will go to 0, and then this means the bolometer is saturated and it stops to behave normally. Okay? So a little bit more on the electrothermal feedback. So the bolometer is basically a system that will give a response in current to a signal in power. So its response is the derivative of the two, di over dp. Okay? So let's calculate that. Remember that in the electrothermal feedback, we have the total power of the bolometer, which is constant, so we can differentiate with respect to I, and we get 0. And because the total power of the bolometer has these two terms, we have this and this, which sum to 0. Of course, the derivative of the electrical power with I is V, because the power is V multiplied by I. Okay? So this means that the response of the bolometer, if you make the calculation, di over dp, because this guy is V, well, the response is -1 over V, which is very good because V is constant. That means that the response of the bolometer is linear and exactly equal to the inverse of the bias voltage. So that's a very nice property. One other property that we could discuss, but we will not do the calculation, it's more complicated, is that the electrothermal feedback will reduce the effective time constant of the bolometer by orders of magnitude, so that the bolometer becomes a very fast detector. So this is found in a historical paper by Adrian Lee and Paul Richards back in 1998. And on this plot here on the right, you can see the efficiency of the electrothermal feedback L, and on the y-axis you can see the time constant of the bolometers, and these are actual measurements. And you can see that the higher the efficiency of the electrothermal feedback, the faster the bolometer. On the other plot, here is the response of the bolometer, the intensity that is measured, the output of the TS, as a function of the power dissipated in the bolometer with a heater, but it would be the same with optical power. And you can see that there is a very good linear response that is exactly 1 over V, the bias voltage of the bolometer. So in the ETF mode, bolometers are both linear and very fast, which is very, very good for scanning the sky with a transition edge sensor. Okay, one complicated issue with bolometers is their microfabrication. One great thing is that one can fabricate bolometers as full arrays, many bolometers on the same wafer. Here you have 256 cubic bolometers that are fabricated all together on an array, but the fabrication is very complicated. It's a succession of many steps that are done in a microfabrication facility, which is a clean room with very complicated machines. And one has to successively deposit layers of different material. Here you see that you have very different materials that are deposited in very, very thin layers of 0.1 to 0.5 micrometer thickness. And one uses different machines to deposit them with masks and things. It's rather complicated, and at the end you have basically 100 steps to fabricate a bolometer. So here you can see these different layers shown here. So that's the absorbing grid, the thermometer, and the grid, and so it's rather complicated. Okay. So this is a zoom on one of the bolometers. You can see the grid here. The readout, so that's the thermometer at the center, which is read through these very small lines here that you can see as well in this zoom here. And all of this is very fragile as it is suspended and only held by these thermal links here to the heat sink, basically. Okay? So that's how it looks like, at least for the cubic TS. So let's try to understand a little bit what is the noise in a transition edge sensor. So usually in a detector, you measure the noise through a quantity that is called the noise equivalent power, the NEP, which is basically the variance of the noise that is dissipated in 1 second. Okay, so this is in watts per root hertz. In a bolometer, there are two contributions for the intrinsic noise of the bolometer: the Johnson noise and the phonon noise. So the Johnson noise is basically the thermal noise for the electric carriers, the electrons in the resistor. So that's the vibration, thermal vibration of the electrons. The phonon noise is some random exchange of phonons with the bath, and is basically the vibration of the crystal that constitutes the bolometer. So the formulas for these two contributions are here. We will not discuss them, but what I want you to see here is that they both depend on temperature, and they will reduce if temperature reduces. So if temperature goes down to 0, these two contributions go down to 0. So that means that bolometers tend to be noiseless when the temperature goes to 0. And that's why we cool down our focal planes down to very low temperature of between 100 and 300 millikelvin. So here is a measurement, an actual measurement of the noise with one of the cubic TES. And you can see the phonon contribution in green here. So the data is in black, and that's the model of the phonon noise. And here in yellow is the model of the Johnson noise. And you can see that the bolometer is rather well modeled by the two contribution. It's not perfect, but it's quite good. Okay, and that's as a function of frequency. So you see that the phonon is slower and happens at lower frequency, while the Johnson noise happens at higher frequencies. So when you're observing the sky with a detector, you collect CMB photons, but not only CMB photons. You also collect thermal radiation from your instrument, and if you're on the ground, you will also collect thermal radiation from the atmosphere. So the optical power that comes in your bolometer is that of the CMB, but also the power from the rest. Okay. So in the case of a ground-based instrument, basically the power you collect from the CMB is 0.4 picowatts, very small, while the total optical power is more of the order of 10 picowatts. So you have a lot more photons coming from the atmosphere and the instrument. And these incoming photons, all of them here, they also fluctuate. This is called background fluctuations. So in the case of the CMB, this power here corresponds to about 10 to the 10 CMB photons. Okay, so you have even much more when you account for everything. So there are two intrinsic fluctuations of this signal. First, the Poisson fluctuation of the number of photons that you receive per second. This goes like square root n. And there's a second term, which is called the bunching term, which is some quantum effect related to the Bose-Einstein statistics, the fact that photons come by groups, bunch. And at the end of the day, the total photon noise is the quadratic sum of these two terms, which you can see here and which we will not discuss in detail. Okay? But finally, the total noise of the bolometer is going to be the quadratic sum of the intrinsic noise of the bolometer and the photon noise. Okay? So we come to the idea of what we call background limited bolometers. Again, the total noise is the quadratic sum of the two. Here are typical numbers. So 0.4 picowatts for the CMB, 10 picowatts for the total from the ground. This corresponds to this big amount of photons and this kind of noise equivalent temperature in watts per root hertz. Okay? So now, if your bolometers are cold enough, you remember that we have seen that the detector noise goes down with temperature. So if the detectors are cold enough, or if your background is small enough, then you can achieve a situation where you have negligible detector noise, where the noise equivalent power from the bolometer is lower than the intrinsic noise of the signal you're looking at. This is called background limited bolometers, and the amazing thing here is that you cannot have a measurement that is less noisy than this, okay? Because your detector noise is negligible. In order to achieve such small noise equivalent power for the bolometer, you need to cool them down below 350 millik typically. So that's why we have this constraint and many constraints coming from this cryogenics. One of the first constraints here is the readout of the transition edge sensors. So if you have NTS that you can see here, well, you have this many electric lines that are the voltage biasing lines that are connected to the 300K. And that's a huge thermal link and with so many cables, even very small cables, you will never be able to reach 0.3 Kelvin for your focal plane. So the only way to do that is to do multiplexing, just like the internet provider does, to provide you video, internet, hundreds of TV channels in one optical fiber. Okay? So here we use cables and multiplexing on the electric signal, which can be time domain and frequency domain. There are advantages and drawbacks for both. But basically, the multiplexer needs to be called, otherwise it will not work. Okay? And you may know that the traditional electronic, which is based on CMOS technology, does not perform well at low temperature. So we have to use another technology for this electronics here. Okay? So we have to build a microprocessor not based on CMOS technology. And in the case of, so that's called an ASIC with another technology. And in the case of Cubic, we use time domain multiplexing based on silicon germanium ASIC and squids here that are used as switches and preamplifiers for the signal. With all this system, we can reach a 128 to 1 multiplexing factors, which is one of the best in the world. And at the end of the day, you have very few wires that connect your cold stage to your room temperature stage, and you can reach the temperature at your focal plane. But that's very heavy and very complicated. So let's try to see a few examples of bolometers, and you will see that there are many different designs and choices for bolometers, for TS. So the original one are the spiderweb bolometers that were very successfully used in the Planck satellite. They were designed back in 1996, basically. There are two designs shown here. The first one is polarization sensitive, and you can see here the spiderweb shape of the absorber with the thermistor at the center. This is about 1 centimeter, pretty big bolometers. Each bolometer is placed at the end of this horn, which is basically an antenna that focuses the signal, that collects the signal. And the shape of the absorber as a spider web is actually designed in order to reduce the sensitivity to cosmic rays, which will have an effective frequency much smaller than the hole between the grids here, so that they pass through in most cases, while photons, which have the wavelength corresponding to the size of the bolometer, will be absorbed. Second design here are polarization sensitive bolometer, where gold is deposited only along one direction, so that they're only sensitive to one given polarization. And you can superimpose the two orientation together in order to measure both polarization, and they're placed as well at the end of these horns. Okay, you can see the legs here that suspend this bolometer, very fragile. In Cubic, we have already seen the bolometers, but that's the opportunity to show you the design, basically, of the instrument, where you have different shields for the cryostat. The outer shield, which is a box in which we make vacuum, is at 300 K, so that's room temperature, it touches the outside. Then you have an inner shield at 40 K that prevents the 300 K radiation, thermal radiation, to come to the inner part of the cryostat. Another shield at 4K prevents the radiation from the 40K to come in. And then inside this 1 Kelvin box, you have the mirrors, the detectors that are shown here. And finally, the detector stage here is at 300 millikelvin, and you can see it here where you have part of the multiplexing devices that are installed here, and you see that you have various arrays of bolometers that are zoomed in here. Okay, so this is a very nice design that was done for the Polar Bear CMB instrument about 10 years ago, and here you see that it's a combination of electric and optical detection, in the sense that you have antennas here. So the radiation is detected in an antenna here. So is an electric signal that goes through these superconducting lines, transmission lines, on which you have filters that are installed here. So all of this is very tiny, okay? 0.5 millimeter here, very, very small. So you have these filters that allow you to select the wavelength you want, and you have a response that is very well established in frequency. And then the bolometer is at the end of the line here. So the energy that is captured here is dissipated here after being filtered. So that's a very nice design, very, very clever and very interesting. Even more amazing is this kind of design where you have actually a trichroic bolometer, where you have this antenna here that selects a very broadband signal going from 90 gigahertz to 220 gigahertz. Then the signals, and in both polarizations, sorry, and then the signals are split here into 3 parts using filters, so that at the end you have 3 bolometers on the same antenna, 95, 150, and 220. And you have an array of these guys, and you see that you can detect in 3 bands altogether. So this is absolutely impressive. Very, very nice design for the South Pole Telescope, 3rd generation. So this is the end of this talk. So in summary, bolometers are very nice detectors that measure the heat deposited by whatever comes into an absorber. They have the advantage of being very versatile detectors, which can detect dark matter particles possibly, but also radiation like CMB, but also X-rays or whatever. They offer an extremely large bandwidth, which allows to have a higher sensitivity because you collect more photons. They're not too sensitive to the background level, especially if you're in a strong electrothermal feedback with TS, because you're stabilized into the transition. And as we have seen, they're extremely sensitive when they're cooled down to very low temperature, because their intrinsic noise can become smaller than the intrinsic fluctuations of the radiation you're looking at. And one has to bear in mind that the very impressive achievements that were done on the CMB observation over the last decade are mostly due to the progress in bolometers. Okay? But also they have disadvantages. The involved cryogenics is very constraining, very heavy. The readout is very complicated. And the microfabrication is a complex process, but it allows for large array production, so you can produce many bolometers at a time. So now the ones I described here are not the only ones, and there are some other kind of designs that I didn't discuss here. And one of the very interesting design that is now becoming more and more fashionable is MKITs, millimeter kinetic inductance detectors, that are a very interesting new alternative because they offer similar noise properties while being much easier to read out and to fabricate. But I will not describe it here. So thank you for your attention, and goodbye.